Dear colleagues, this work provides a structured overview of how current research paradigms are evolving and what that means for the future. Each image represents a case study showing how digital tools and military-grade equipment serve defensive, ethical, and humanitarian purposes. This research particularly introduced an adaptive framework for mitigating low-frequency noise in software-defined radios using extended feature information matrices and Kalman filtering. Here we compare SDR performance with and without FAIM guided Kalman filtering, showing significant gains in noise resilience and signal clarity. Bit error drops from 12.5% to 4.2%, and SNR improves from 25 to 40 decibel under FAIM based adaptation. While Villa's DT study focuses on RF modeling and synchronization, our approach integrates FAIM and Kalman filtering for real-time noise adaptation. Unlike the Coliseum DT, our method achieves a 40% improvement in SDR signal detection under noisy conditions. Extended FAIMs and dynamic Kalman updates enable real-time tuning, which was not addressed in the baseline DT approach. The CAST workflow enables scenario generation by combining 3D modeling, ray tracing, and emulation, essential for realistic SDR testing. We modeled the key performance indicators SNR, BER, and delay using a structured data matrix for FAIM guided optimization. Our adaptive SDR system cuts jamming response time from 250 milliseconds to just 90 milliseconds, enabling faster threat detection. Bit error rate drops by over 60%, while SNR improves significantly, showing clear gains in signal quality. In terms of packet loss, we have a reduction by 30%, confirming the resilience of FIM guided filtering under variable noise. Time-based heat maps validate consistent improvement in SINR and true output, even under dynamic conditions. So questions are now, what kind of noise is happening here? Which and where is it coming from? Which noises matter the most? By systematically gathering this information, the SDR can quantify how much each noise source degrades signal performance and determine which interference type should be mitigated first. Instead of randomly adjusting its signal, the SDR uses FIM to prioritize problems, ensuring that the most critical interference sources are addressed first. Different noises impact SDR performance in a specific way. Echoes and soil absorption are particularly harmful and require frequency or with pattern adjustments. In AOI1, using FIM and Kalman filtering, we observed a stronger signal with higher PSD and 40% SNR improvement compared to the standard mode in AOI2. The adaptive method offers better jamming resistance and robustness. The red and blue curves show how adaptive filtering smooths the signal response and minimizes variance under real-world noise. Compared to static systems, the FIM-Kalman model offers dynamic adaptation, reducing BAR by up to 20%. Signal-to-noise ratio becomes more stable, up to 40% improvement under variable noise conditions. Response latency drops below 100 milliseconds, allowing real-time reaction to interference. Unlike fixed parameter SDRs, this architecture dynamically tunes itself to environmental factors, improving both stability and energy efficiency. These equations formalize how Fisher information and Kalman filtering interact to optimize the signal estimation and system identification. Equations 16 and 17 quantify the sensitivity of system parameters, while 18 and 19 update the prediction and correction stages in real time. By embedding this logic, SDRs can dynamically respond to complex interference, ensuring a more robust and adaptive performance. This final slide highlights the core covariance structure of the FIM-Kalman model, linking signal parameters to estimation accuracy. By integrating CRLB and covariance terms, we enhance SDR resilience across variable noise and multipath conditions. These matrices serve as the mathematical backbone, enabling real-time signal optimization and adaptive filtering. In essence, FIM-Kalman blends statistical estimation with system dynamics for robust SDR decision making. Here we compare field-based FIM matrices from two archaeological sites, assessing how terrain affects SDR optimization. Suggestion shows higher matrix asymmetry, indicating more signal distortion due to structural scattering and material interfaces. Selinunte, by contrast, yields more consistent FIM values, reflecting smoother propagation paths and less multipath interference. This terrain-aware approach helps tailor SDR filtering strategies for site-specific signal condition. These sensor maps show indeed how local terrain variability affects signal estimation across different spatial clusters. FIM parameters highlights, on the other side, variations in signal phase, roughness, and distance-dependent noise, especially in cluster 2 with higher instability. The infinity value for cluster 2 in Selinunte indicates excessive environmental interference or sensor saturation. By combining spatial clustering with such metrics, we applied GMM clustering to model interference distribution over this suggests and Selinunte difference. Each ellipse represents a probabilistic interference zone, supporting terrain-aware SDR adaptation strategies in high variance and or phase distortion. The heat map, which visualizes the spatial distribution of normalized signal power, with most areas falling below the 0.4 thresholds. The mean power level, mu1, equivalent to 0.327, confirms that this site suffers from generally weak signal propagation. Kalman filtered estimates helping smooth short-term fluctuations. And the second scenario with mu2 equivalent to 0.452. Fewer low power zones are represented with more stability. And how signal power varies across frequency bands. Red traces indicate stronger responses compared to the blue reference. The time domain and frequency domain comparison reveal sharper peaks in the red signal, indicating amplified propagation effects. The delta mu is equivalent to 0.125, with a vertical dispersion. The findings in last instance validate that FAIM Kalman SDR architecture significantly outperform traditional SDR systems, as evidenced by higher spectral efficiency, robust real-time adaptation, superior jamming resistance, improved signal stability across spatial domains, confirmed through GMM. As wireless technology evolves, adaptive SDR architecture will become indispensable, paving the way for more intelligent, interference-resistant, and communication systems. Thank you for your attention. We appreciate your appreciation and participation. Goodbye.